ready because we're diving deep into the quantum world.
A world where things aren't always as they seem.
Exactly. And today, we're tackling a question that's trickier than it sounds. What makes something quantum?
Yeah, it's a question that's had physicists scratching their heads for ages.
Especially when it comes to a property called spin. We've got research papers, historical accounts, anecdotes, and it all points to one pretty mind-blowing conclusion about quantum spin.
You know, it's fascinating. Even seasoned physicists get this wrong.
Really?
Yeah, you look at spin and you think, okay, tiny spinning top, we can explain that. Classical physics, right?
Right.
But that's not the whole story. Not even close.
It's like one of those optical illusions. You think you see one thing, but then your brain flips the image.
Exactly. And today's deep dive, well, it's all about that flip, that change in perspective. We're exploring how some groundbreaking research has finally proven a theory about quantum spin that's been ignored for years.
A theory that could change everything.
Yeah, fields like quantum computing and sensing could be revolutionized.
So we've got mystery, we've got potential breakthroughs, we've got some seriously counterintuitive physics. I love it. But let's set the stage first. This concept goes back to 1925, right?
Right. Two young physicists, Samuel Goudsmit and George Uhlenbeck, proposed this radical idea. Electrons, those tiny particles that are constantly whizzing around atoms, they're actually spinning.
Like little tops.
Exactly. Little spinning tops. You got these electrons, the building blocks of matter, and they're constantly in motion. Spinning, spinning, spinning.
I remember learning about this in school. Thought it was pretty cool back then.
I bet not everyone was thrilled about it at the time, though.
That's true.
It caused quite an uproar. Big names in physics, people like Hendrik Lorentz, they were really critical.
Really?
Oh, yeah. But Goudsmit and Uhlenbeck, they had a supporter in their corner, Paul Ehrenfest. He encouraged them. He even told them, "You are both young enough to be able to afford a stupidity."
That's a great quote.
Yeah.
I love that. It just goes to show you, sometimes scientific progress needs that boldness, that willingness to challenge what everyone thinks, even if it seems, a little stupid at first.
Absolutely. And, even though spin eventually became accepted as part of quantum mechanics, that misconception about it being easily explained by classical physics, well, it kind of stuck around, even made its way into modern textbooks.
It's like a game of telephone. The message gets distorted along the way. But this time, the telephone is decades of scientific literature.
Such a good analogy. And that's where Boris Tsirelson enters the picture. Decades after Goudsmit and Uhlenbeck proposed spin, Tsirelson came up with a theoretical protocol. This protocol challenged that assumption that we can't see the quantumness in a spinning system. He thought we could, under the right conditions.
Okay, but I'm sensing a but here.
You're right on the money there. Sadly, Tsirelson's work was largely ignored at the time. It wasn't until much later that Tsirelson-Scarani and his student Zalin H2 rediscovered it. They saw its potential.
So they had this theory suggesting spin could be demonstrably quantum, but needed a way to test it.
Right. And they couldn't just use any particle. Needed one with more than two spin states.
Ah, okay.
Think of it like this. An electron's like a coin, right? It can be heads or tails.
Yeah.
But they needed a system that was more like a die with multiple sides.
Oh, okay. More options to see the full range of possibilities, the quantum weirdness. So what did they use?
They went with the nucleus of an antimony atom. Has 8 possible spin directions. And, get this, they put this antimony atom into a Schrödinger's cat state.
Okay, Schrödinger's cat, that's the thought experiment with the cat in the box.
Yep.
Right.
Yeah.
But we're not talking about actual cats here, are we?
No, not actual cats, no. It's a thought experiment, but a powerful one. It helps to understand the crazy concept of superposition in quantum mechanics. So in this case, they basically made the antimony atom spin in multiple directions at the same time.
Whoa. Okay. That's a lot to take in. So they've got this antimony atom spinning in multiple directions at once. How does that prove anything about spin being quantum?
That's where the Tsirelson-Scarani protocol comes in. They measured not just the average spin direction, but also its positivity. A way of quantifying how much the spin is behaving in a truly quantum way.
Positivity. I'm going to need you to break that down for me.
Okay, so imagine this. You measure the spin of a bunch of particles in the classical world. The average spin will always be within a certain range.
Mm-hmm.
But in the quantum world, thanks to superposition and all that weirdness, the average spin, it can actually go beyond that range.
So it's like a quantum speedometer.
Exactly, measuring how quantum the spin is.
And did they break the classical speed limit?
They absolutely did. Their measurements provided what they called unquestionable evidence for the quantumness of the antimony spin.
Okay. I think I see what's going on here.
They
They
said
took this forgotten theory, designed this clever experiment, and actually proved that spin is not just some classical spinning motion, it's something fundamentally quantum.
exactly, which changes everything, because now we know for sure even a single spinning particle can exhibit behavior that defies classical physics. And that opens up a whole world of possibilities.
And speaking of possibilities, I'm guessing this research has some pretty big implications, things like quantum computing, right? But before we get into that,
Yeah, huge implications. In fact, those specific quantum states they use, the ones that showed undeniable quantumness, they offer advantages in quantum computation and sensing.
so we've been in the theoretical weeds here, this mind-bending nature of quantum spin. Let's talk about real-world stuff. How does this translate into applications?
Imagine a computer that can solve problems in seconds. Problems that would take our best supercomputers millions of years. Or sensors so sensitive they can pick up the faintest whispers of gravitational waves. It gives us a new way to see the universe. That's the kind of power we're talking about when we harness quantum phenomena, superposition, entanglement, all of that.
Okay, I'm sold. Sign me up for the quantum revolution. But can we get a bit more specific? How do these quantum states, the ones with the antimony atom, how do they give us an advantage in computing and sensing?
Think back to that antimony atom spinning in multiple directions at the same time, right? That's superposition, and it allows a massive amount of information to be encoded in a single particle.
So it's like a computer bit that can be 0, 1, and everything in between, all at the same time.
Exactly, you got it. And when you have a system that can exist in so many states simultaneously, you can do computations in parallel, on a scale that dwarfs anything a classical computer can handle.
It's not just about speed. It's a whole different way of thinking about computation. But what about sensing? How does quantum spin help us build better sensors?
Let's take magnetic field sensing as an example. Say you have a system, like an atom that's been prepared in a specific way, a fragile quantum state. Any tiny change in the magnetic field around it will disrupt that state, and we can measure that disruption very, very precisely.
So it's like a super sensitive alarm system. But instead of a burglar, we're detecting tiny changes in magnetic fields.
Exactly. And this applies to more than magnetic fields. We could build quantum sensors for gravity, temperature, rotation, you name it. This has the potential to revolutionize everything: medical imaging, navigation, even our basic understanding of physics.
It's mind-blowing, really. But I have to ask, every new technology has its downsides. How do we make sure this quantum revolution benefits all of humanity, not just a select few?
It's a crucial question. Quantum tech is powerful, and with great power comes great responsibility. As we develop these technologies, we have to think carefully about the ethics involved and make sure they're used responsibly, for good, not for harm.
Agreed. We need to guide this technology down the right path. But for now, let's just appreciate the wonder of this discovery. From a basic question about spin to a potential technological revolution, that's the power of scientific curiosity.
Absolutely. And this research is just the tip of the iceberg. So much more to explore in the quantum realm.
Speaking of exploring what's next, what are the challenges in making these theoretical possibilities into reality?
One of the biggest hurdles with quantum computing is scalability. Building systems with a large number of interconnected quantum bits, or qubits as we call them, it's incredibly complex. It's not just about creating these delicate quantum states, it's about controlling them, manipulating them, and preventing them from collapsing before you can get any useful information out of them.
So it's like trying to build a house of cards in a hurricane.
That's a great way to put it. That's why researchers are exploring all these different ways of building qubits, from trapping ions to using superconducting circuits. And you know what? The insights from this spin research, they could help us optimize these systems, make them more stable, less prone to errors.
And what about quantum sensing? What kind of advancements can we expect to see in the near future?
I think we'll see these sensors becoming more and more sensitive, and smaller too. Imagine portable devices for medical imaging that can detect diseases really early on, or quantum sensors that monitor environmental changes with incredible precision, giving us valuable data for climate change research, for example.
It feels like we're on the cusp of something truly revolutionary, a quantum revolution. But before we get lost in the possibilities, I want to go back to something you said earlier about the weirdness of the quantum world. It makes you think. If even something as basic as rotation can be quantum.
What other hidden quantumness might be out there, lurking in the everyday world?
Precisely. Makes you question everything you thought you knew.
And that's the beauty of it, that sense of wonder. It drives scientific discovery. Who knows what mysteries await us as we keep digging deeper into the quantum realm?
Well, on that note, let's shift gears a bit. I want to dive into some of the philosophical implications of all this. Because if even something as ordinary as rotation can defy classical physics, what does that tell us about reality itself?
Yeah, it's a really big question, one that physicists and philosophers have been wrestling with for ages. The more we learn about the quantum world, the more we realize how little we actually know.
And how much it challenges our everyday understanding of how things work.
Right, it just doesn't fit with our intuition. Let's break it down a bit. What makes quantum mechanics so different from the classical physics we see around us?
One of the key differences is this idea of determinism. In classical physics, if you know the starting conditions of something, you can pretty much predict how it's going to behave with certainty.
A clockwork universe. Everything ticking along predictably.
Right. But the quantum world, it's way fuzzier,
Hmm.
much less predictable. So instead of certainty, it's all about probabilities.
Right.
Things could go this way or that way.
Yeah, and this probabilistic nature, it has some pretty big implications. For example, it suggests that just by measuring something, we might actually be changing it.
Hold on. You're saying just by looking at something, we change it.
It's one of the biggest mysteries in quantum mechanics, the measurement problem.
It's pretty wild.
Yeah,
Makes you question whether there's even an objective reality out there.
right. It challenges that whole idea of a reality that exists independently of us observing it. Some interpretations even suggest there are multiple realities, and when we measure something, we're basically forcing it into one of those realities.
Multiple realities. So like a multiverse where every possibility exists.
That's one interpretation, but there are many others. The truth is, we don't really have all the answers. Quantum mechanics gives us a way to understand the universe at its most basic level. But it also opens up all these philosophical questions we may never be able to fully answer.
It's both exciting and kind of unsettling, knowing how much we don't know. But I guess even if we can't answer these big questions definitively, just asking them is a step forward, right? Makes us think differently about our place in the cosmos.
Couldn't agree more. Studying quantum mechanics forces us to confront the limits of what we know and to really appreciate the mysteries of the universe.
And that brings us right back to this research on quantum skin we've been discussing. It's not just about technology. It's about changing how we see the universe.
Absolutely. It makes us rethink what's possible and embrace the strangeness of the quantum world.
So as we wrap up this deep dive, what's the biggest takeaway for our listeners? What should they be thinking about now that we've thoroughly bent their minds with quantum spin?
Well, I'd say the next time you see something spinning, whether it's a top, a bicycle wheel, even the Earth itself, remember this. Underneath that everyday motion, there's a whole world of quantum wonder.
It's amazing to think about.
A world where particles can be in multiple states at once, where observing something changes it, and where the very definition of real is still up for debate.
That's a perfect way to put it. And on that note, we'll bring this deep dive to a close. We've explored the history, the science, the philosophy of quantum spin. It's been a journey into a world where the familiar meets the truly bizarre. Until next time, folks, keep questioning, keep exploring, and keep being amazed by the mysteries of the universe.